Okay, what we're going to do here is we're going to continue talking about basic science. And specifically, in this lecture, we're going to be talking about atoms and elements. So to begin, we're going to define what an element is. So an element is a substance that can't be broken down by chemical means. And we want to highlight the chemical means part of this. So what this basically says, what this definition says, is if I have a block of sodium, and no matter how I cut it, I can bombard it with like electricity, I can put acid, put a base, okay, it's still going to be sodium. Okay, I'm still going to have sodium. Okay, I cannot change the element sodium using chemistry. Water, okay, water's chemical formula is H2O. Now, if you do chemistry, you can do some chemical reactions of water, and it will break this into its component parts. Oops, I don't want to do that. I can break this into the component parts. Okay? Hydrogen and oxygen. Water is not an element. It's not an element. Okay, water is a molecule. Okay, but I can take that molecule and I can break it into its component parts. Okay. Right? So hydrogen is an element. Oxygen is an element. Okay. I cannot break, using chemistry, the elements into other things. Okay. Now, elements are important for us because we need them in order to live. And our body is composed of elements. Okay. So some of the elements that you're going to need to know that make us are the major elements and the trace elements. Okay, so the major elements, you need to know the big four. The major elements. And those are oxygen, carbon, hydrogen, and nitrogen. Okay. There are others. There's calcium, there's phosphorus, potassium, sulfur, chlorine, sodium, and magnesium. Those are all major elements, but these are the big four. The big four: oxygen, carbon, hydrogen, and nitrogen. And they make about 99.9% of you. That's the percentage in your body of these elements. Okay, oxygen itself is like 65%. Okay, carbon is about 18%. Hydrogen is, I think, 9.5%. Yeah, 9.5. And nitrogen is like 3.2%. Okay, so if you total these up, you see that it doesn't equal 99% because I've dropped the other ones. When these are the big four. I call these the big four. These are the big four. Okay, and then we have the trace elements. So you need these to live as well. So don't let anybody tell you that you don't need elements, because you do. You just don't need these guys as much. And trace elements, all of them together, all the remaining, it's like 0.1% of the percentage. And some of these are like copper, fluorine, iodine, iron, etc., etc., etc. Okay, the big ones you're going to want to basically remember are iodine and iron, especially for anatomy and physiology, because you need iron for your blood to work. If you don't have iron, you don't, your red blood cells won't work. And iodine, if you don't have iodine, your thyroid hormones won't work. Okay, so those are the elements, and that's what elements are. So now, the other thing we're going to talk about here is atoms. Atoms. So atoms are the smallest units of an element that retain the properties of the element. Okay. And we want to do this. Retain the properties of the element. Because I know some people who watch this are going to be like, well, they're not the smallest. Well, I know that they're not the smallest, but the smaller elements of an atom do not retain the properties of the elements that they represent. Okay, so an atom is the smallest unit of an element that retains the properties of the element itself. Okay, so now atoms are actually built of smaller units called subatomic particles. Okay, they are built up of subatomic particles. Okay. And there's only three that you need to worry about in a beginning anatomy and physiology class. The first is a proton. Okay. Now a proton has mass. It has a weight. We call it 1 AMU, atomic mass unit. Okay. It has a charge. It has a positive charge. Okay. So a lot of time what we do is we just notate that as a plus sign, positive charge. Okay. And it is in the nucleus. Of an atom. Okay. And we're going to put a little star next to this one. I'm going to do it in red. Little star right here, and it determines element's type. Okay, and I'm actually going to underline that as well. It determines the element type. So you've seen the elements we talked about, the big four: oxygen, carbon, hydrogen, and nitrogen. Oxygen has a different number of protons than carbon. Carbon has a different number of protons than hydrogen. Hydrogen has a different number of protons than nitrogen itself. So the difference between them is the number of protons and, to an extent, the number of neutrons inside of the nucleus itself. It is the proton that determines the proton and the number of protons that determines the element type. Okay, protons in the nucleus determine element type. Okay, the second subatomic particle we're going to talk about, number 2, it is called a neutron. Okay, it is basically pretty much the same thing as a proton, but it has no charge. It has no charge. So it has got a mass of 1 AMU, atomic mass unit. It is no charge. It is neutron. It is neutral. And where does it live? It lives in the nucleus of an atom. Okay. And what does it do? It stabilizes. The nucleus. And I'll explain what I mean by this when we actually draw out a model of an atom. And then we have the third subatomic particle. It is the electron. Okay. We ignore the mass of an electron. So we just say no mass, because it is so small that it's virtually weightless. I mean, it does have a mass, but we don't use it to use any calculations. Okay, it has a negative charge. Okay, we write that as a minus, and it is around the nucleus. Okay. And what the electron does, they allow atoms to interact with each other. Okay. So atoms, smallest units of elements that have the properties of the elements. Atoms are built up of subatomic particles, protons, neutrons, and electrons. So now what we're going to do is we're going to do this thing called a Bohr model of an atom. And just to show you how we can visualize them. So atoms, like we said, they have protons in the middle. And so you have a proton. Now, if you have one single proton in the middle, in the nucleus of an atom, no big deal. No big deal. Now, the problem is, what if I have two protons sitting next to each other? So a positive charge right next to a positive charge. Okay. You ever, when you were younger, put magnets next to each other? So if you have a magnet right here, and it's got the negative end here, and it's got the positive end here, and it's got the positive end here, and the negative end there. Okay. What do they want to do? Are they attracted to each other? Okay, no. The same charges will repel each other. Okay, positive charge is going to repel each other. So now what's going to happen if I take two protons in this nucleus and I put them next to each other? They're going to want to split. Okay, that's it. So that's what the neutron is for. Okay, so if I need more than one proton sitting inside of this nucleus, I've got to have a proton. And then I have to have, I'm going to draw it in a different color. That's blue. It's chill. It's blue. Put a 0 in there for no charge. I've got to have a neutron. Neutron in here. And then I can put another proton in there, like that. Okay. So the way I think of neutrons, it's like the marriage counselor. Okay, so you've got this proton wants to split, and this proton wants to split if they get too close to each other. And what the marriage counselor does is it keeps them close enough together to where they just don't automatically split. Okay, it's a buffer zone. That's how it works, and that's what the proton does. And so if you didn't have, that's what the neutron does. If you didn't have the neutrons sitting in the nucleus, the positive charges would repel each other, out, and the nuclei would break themselves down. Okay, so now there's an interesting thing about this is that there has to be a perfect space. It has to be a perfect space. You can't push them too far away. So neutrons, you can have too many neutrons inside of a nucleus, where the nucleus will break apart because there's just too much space between them anyway. And we'll talk about that when we talk about radioisotopes. But in general, right now, all you really need to know is the neutrons. What they do is they stabilize the nucleus. They prevent the positive charges from repelling each other and breaking down the nucleus. Okay, so that we've dealt with protons, we've dealt with neutrons. Now, spinning around the nucleus. Oops. Okay, I'll do this. Let's put a different color. Let's do it. let's do it in this green color. So spinning around the nucleus, you have these little negatively charged things called electrons. Okay, this is what's, like I said, this is called the Bohr model. Okay, it shows the neutrons and the protons inside the nucleus, and spinning around them are the electrons. How it actually is, though, is you've got a nucleus sitting here, and you've got positive and you've got negative charges in here. So you've got some positive neutrons sitting in here, all clumped together. And then you have this thing, I got to use a pencil to do it. You have this thing around it. See how hazy that is? It's not it's called an electron cloud. It's actually an electron cloud. So the electrons just zip around this thing in a cloud. So it's not, while there are distinct energy levels of them, the electrons just spinning around in this cloud around the nucleus, not necessarily 100% all the time in its own isolated path. Okay, but we like to think about them as in an isolated path, but they're not totally 100% of the time. Okay, and so that's it. That's the model. So that's what we wanted to do right now for this, and I think we've got a good basic understanding of how we can actually talk about how atoms will interact with each other in the next couple of lectures, and how bonds occur, what types of bonds and reactions occur. And with that, I think we are done. Thank you.